Somewhere beyond Mars, an object is doing something it absolutely should not. 3I Atlas, an interstellar intruder, has begun unfolding, blooming into a structure nearly 1,000 times larger than when it first entered our system. Two colossal tails, nearly 3 million kilometers long, reach toward and away from the Sun, as if signaling someone or somewhere. Its material jets are so dense they overwhelm the solar wind. Stefan Burns calls it rapidly growing larger. Avi Loeb calculates that at this rate, it's losing nearly all its mass every month, as if burning through its own body. With odds of such an object appearing naturally pegged at 1 in 100 million, scientists are now asking whether this is the most extreme comet ever seen, or something far more extraordinary. Stay until the end as we explore the images, the data, and the probable scenarios of what could happen next, because this might just be the beginning of something none of us is ready for. On November 9, 2025, two amateur astronomers pointed their telescopes at a tiny speck of light drifting through the outer solar system. What they captured would stop professional scientists in their tracks. Frank Niebling and Michael Buchner, working independently with specialized equipment, began their imaging sequence at 5:08 Universal Time. By 5:22, they had documented something that shouldn't exist according to everything we know about comets. The object known as 3I Atlas, an interstellar visitor that had been quietly drifting through our cosmic neighborhood for months, had suddenly exploded in size. Not doubled, not tripled, nearly 1,000 times larger than it appeared just weeks earlier. Let me be clear about what 1,000 times means. Imagine looking at a basketball, then turning away for a moment, and when you look back, it's the size of a shopping mall. That's the scale of transformation we're talking about. This wasn't a gradual expansion. This was an eruption of material so violent and sudden that it rewrote the rules of what interstellar objects are supposed to do. The images show something that looks less like a comet and more like a cosmic explosion frozen in time. Two massive jets of material stream away from the tiny nucleus, one pointing toward the Sun and one pointing away from it. The anti-sunward tail, the main structure extending behind the object as it moves, stretches across 30 arc-minutes of sky. That's the same apparent size as the full moon, but here's where your brain needs to adjust for scale. The moon is 384,000 kilometers away. 3I Atlas was 326 million kilometers from Earth when these images were captured. At that distance, 30 arc-minutes translates to roughly 2.85 million kilometers of physical length. That's nearly 3 times the diameter of the Sun. Think about that. 3 times wider than our star. A tail of gas and dust streaming through space at distances where sunlight takes almost 20 minutes to arrive. And it's not just one tail. The jets point in opposite directions, sunward and anti-sunward, defying the simple physics we teach in high school astronomy classes. Frank Niebling used a Tech 140mm telescope with an f/5 focal ratio, paired with an ASI 6200mm camera. Michael Buchner employed similar equipment. These aren't billion-dollar space telescopes. These are instruments you could theoretically buy if you saved up enough money and had a serious obsession with the night sky. Yet, they captured something that's forcing Harvard astronomers and geophysicists to question fundamental assumptions about how matter behaves in space. The color in these images isn't arbitrary. It's not artistic enhancement. Different wavelengths reveal different chemicals being ejected from the nucleus. The jets show structure, density variations, curves and bends that suggest complex forces at work. And those anti-tails, the jets pointing back toward the Sun, they shouldn't be there. Solar wind, the constant stream of charged particles flowing outward from our star at roughly 400 kilometers per second, should blow any gas or dust away from the Sun. It's like trying to spit into a hurricane. The material should be ripped away instantly, scattered into the void. But these anti-tails persist. They curve. They maintain coherence across millions of kilometers. Geophysicist Stefan Burns looked at the data and confirmed what everyone was thinking, but hesitant to say out loud. The tail is rapidly growing larger, not slowly accreting material. Rapidly. Day by day, the structure expands. And this brings us to the question that's keeping astronomers up at night. Where is all this material coming from? Harvard astrophysicist Avi Loeb ran the calculations. Based on the observed expansion rate, the density of the material, and reasonable assumptions about the composition of the jets, he estimated that 3I Atlas is losing approximately 50 billion tons of material every month. 50 billion tons. To put that in perspective, that's roughly equivalent to the entire estimated mass of its nucleus. Every month, this object is supposedly ejecting its own body weight into space. Now, comets lose mass. That's what they do. When they get close to the sun, frozen volatiles, water ice, carbon dioxide, methane, they heat up and sublimate directly from solid to gas. This creates the familiar tales we see in textbooks. But comets lose maybe 0.1% of their mass during a close approach to the sun, not 100%, not their entire body every month. 3I Atlas is currently about 326 million kilometers from the sun. That's roughly twice the distance between Earth and the sun. It's not particularly close. It's not being roasted by intense solar radiation. Yet, it's behaving like a comet that's being torn apart by forces we can't identify. Standard comet physics assumes a nucleus, a dirty snowball, that's maybe a few kilometers across. Maybe 10 kilometers for a really big one. The sublimating gases create pressure that pushes dust and more gas away from the surface. Solar radiation pressure, the physical push of photons from the sun, then shapes this material into a tail. Solar wind, charged particles, adds another layer of complexity. Together, these forces create the elegant curved tails we associate with comets. Graceful, predictable, well understood. But 3I Atlas has jets that extend millions of kilometers. The gas density required to maintain coherent structures at that scale, to prevent the solar wind from simply dispersing everything into a diffuse haze, is estimated to be roughly 1 million times higher than normal cometary values. 1 million times. That's not an incremental difference. That's not we need to tweak our models a bit. That's our models are fundamentally missing something. And here's where the story takes on an edge of cosmic mystery. 3I Atlas is the third confirmed interstellar object to visit our solar system. The first was 1I Oumuamua, that strange cigar-shaped tumbling rock that passed through in 2017. The second was 2I/Borisov, a more conventional-looking comet that arrived in 2019. Both were weird in their own ways. Oumuamua accelerated slightly as it left the solar system, a push that couldn't be explained by gravity alone. Borisov had unusual chemical signatures, but 3I Atlas makes both of them look ordinary. The odds of an interstellar object this large, this active, appearing in our solar system have been calculated at roughly 1 in 100 million. 1 in 100 million. And yet, here it is. Visible in amateur telescopes. Growing larger by the day. Defying explanation. So what are we looking at? Is this the most extreme natural comet ever observed? An object that formed in conditions so different from our own solar system that its behavior seems alien? Or are we witnessing something else entirely? Something that wasn't formed by natural processes at all? Before you dismiss that question as science fiction, consider this. Everything we're about to examine, the trajectory, the mass loss, the jet structures, the statistical improbabilities, points toward physics that either requires us to completely rewrite what we know about comets, or accept that we're observing something unprecedented in modern astronomy. And the more data we gather, the stranger it becomes. The first thing that catches your attention when you dig into the observation logs is the color changes. Over the past several months, 3I Atlas hasn't maintained a consistent appearance. Early observations showed a distinctly reddish hue. Then, as it moved closer to the sun, the color shifted to green. Now, in the latest images, there's a blue tint to parts of the jets. This isn't a subtle artistic interpretation. This is measurable wavelength data showing that the chemical composition of the ejected material is changing over time. Red typically indicates carbon-based molecules, dust particles, organic compounds that reflect longer wavelengths of light. Green often points to diatomic carbon or cyanogen, and sometimes ionized carbon monoxide. Blue suggests ionized gases, potentially metal ions, magnesium or sodium, or ammonia reflecting shorter wavelengths. The progression from red to green to blue tells us that either the temperature at the surface is changing, exposing different layers of material, or the nucleus is compositionally stratified, like an onion with different chemicals at different depths. But colors are just the beginning. The real anomaly shows up when you plot the trajectory. Every object in space moves according to gravity. Planets orbit stars, moons orbit planets. Comets follow elliptical or hyperbolic paths determined entirely by gravitational forces. Except 3I Atlas isn't following the path it should. There are deviations, small but measurable changes in velocity that can't be explained by the sun's gravity, or Jupiter's gravity, or any combination of gravitational influences in the solar system. These are called non-gravitational accelerations, and they're not completely unknown in comets. When a comet ejects gas from its surface, that gas creates thrust, like a tiny rocket engine. The comet gets pushed in the opposite direction. For typical comets, this effect is minuscule. It might change the orbit by a few kilometers over months. For 3I Atlas, the deviations are significant enough that orbital prediction models have to be constantly updated. The outgassing isn't symmetric. It's not a gentle, uniform release of gas. It's directional, episodic, powerful. Now let's talk about that 50 billion ton per month figure, because it sounds absurd, and you need to understand how that number is calculated. First, you estimate the density of the nucleus. For most comets, we assume around 0.5 gram per cubic centimeter. That's less dense than water, about the consistency of loosely packed snow. Then you estimate the size of the nucleus from brightness measurements. Based on how much sunlight it reflects, astronomers estimate 3I Atlas has a nucleus somewhere between 5 and 10 kilometers in diameter. Let's say 7 kilometers as a middle estimate. That gives you a volume, and combined with density, a total mass. Roughly 100 billion tons, give or take. Now look at the jets. Measure their brightness, their density, the speed at which material is moving. Use spectroscopy to determine composition. From all of that, you can calculate how much mass is being ejected per unit time. The answer keeps coming back to around 50 billion tons per month. Half the nucleus mass. Every month. This is where conventional physics starts to sweat. If this rate continues, the object should be completely gone in 2 months, vaporized, dispersed into space as a cloud of gas and dust. And yet, the observations from 4 months ago, when Hubble briefly imaged it, showed a faint halo, but no massive jets. Something changed. Something activated. The object went from quiet to catastrophically active in a matter of weeks. Some images show the tail clearly. Others, taken just days apart, show almost nothing. At first, this seemed like instrumental error or atmospheric interference. But the effect is consistent across multiple observers using different equipment in different locations. The tail appears to vanish and reappear. This is likely an effect of viewing geometry. When Earth, the Sun, and 3I Atlas align in certain configurations, the tail might be oriented edge-on to our line of sight, making it nearly invisible. Or the jets might be episodic, turning on and off as different parts of the nucleus rotate into sunlight. The observation geometry matters more than you might think. For months, 3I Atlas was hidden behind the sun from Earth's perspective, lost in the glare. As it emerged from solar conjunction, amateur astronomers started picking it up near Mars in the sky. It's currently moving through the constellation of Gemini, slowly shifting position night by night. Because of Earth's orbit, our viewing angle changes continuously, which means the apparent orientation of the jets changes too. What looks like a single tail 1 week might resolve into 2 distinct structures the next. Cross-validation is critical in astronomy. You can't trust a single observation, especially when the target is faint and the data is noisy. But multiple observers, using different instruments at different locations, are all seeing the same thing. The jets are real. The expansion is real. The flux measurements, the amount of light being emitted and reflected, are consistent across datasets. This isn't a glitch. This isn't a misinterpretation. This is something genuinely happening out there in space. 326 million kilometers away, playing out in real time. The anti-tails are particularly fascinating. Most comets have a single primary tail, always pointing away from the sun because of radiation pressure and solar wind. Some comets develop a secondary dust tail that curves slightly due to orbital motion, but 3I Atlas has prominent jets extending toward the sun. These sunward jets curve slightly, bent by the interplay of the object's motion and solar wind pressure, but they maintain structural integrity across 10 arc-minutes of sky. That's roughly 350,000 kilometers at the object's distance. The main anti-sunward tail, the one stretching 30 arc-minutes, shows internal structure. It's not a uniform stream. There are bright knots, regions of higher density. There are gaps, dark lanes where material seems thinner. The tail isn't straight. It has gentle curves, suggesting complex dynamics in how material is being ejected and shaped by external forces. Arc-minute measurements are how astronomers describe apparent size in the sky. The moon is 30 arc-minutes across. So is this tail. But the moon is close. 3I Atlas is almost 1,000 times farther away. The physical scale is incomprehensible to our primate brains that evolved to understand the size of fruit and predators, not cosmic structures millions of kilometers long. Hubble's observations from 4 months earlier, before the expansion, showed a small, faint coma, the hazy cloud of gas around the nucleus, maybe a few thousand kilometers across. Typical, unremarkable, the kind of thing you'd expect from a distant comet. Then, the explosion happened. The transition from quiet object to catastrophic outburst occurred faster than any known cometary outburst in history. So here's what we have. Color changes suggesting evolving chemistry. Non-gravitational accelerations suggesting powerful, directional outgassing. Mass loss rates that imply the object is consuming itself. Episodic behavior where the tail appears and disappears. Structures that defy conventional solar wind physics. And all of it happening at a distance where comets are usually quiet and inactive. Every piece of data raises more questions than it answers. And collectively, these observations establish that 3I Atlas isn't just an interesting comet. It's something outside the boundaries of what we thought was possible for natural objects. Which brings us to the uncomfortable question we've been dancing around. If conventional physics can't explain it, what can? Let me walk you through the standard model, the one that works beautifully for every comet we've studied in detail, right up until we point our telescopes at 3I Atlas. Comets are dirty snowballs, a mix of water ice, frozen carbon dioxide, frozen methane, ammonia, and various organic compounds, all glued together with silicate dust and rocky particles. They form in the cold outer reaches of stellar systems, where temperatures are low enough for these volatiles to remain frozen for billions of years. When a comet swings close to the sun, solar radiation heats the surface. The frozen volatiles don't melt, they sublimate, transitioning directly from solid to gas. This creates pressure beneath the surface, and eventually the gas breaks through, carrying dust particles along with it. The gas and dust form a coma around the nucleus, a temporary atmosphere. Solar radiation pressure, the actual physical momentum of photons, pushes the dust away from the sun. Solar wind, the stream of charged particles, interacts with ionized gas molecules, also pushing them away. Together, these forces create tails that always point generally away from the sun, regardless of which direction the comet is actually moving. This model works. It explains comets like Halley, Hale-Bopp, Hyakutake, all the famous ones. It predicts tail lengths, brightness variations, chemical compositions. You can write equations, run simulations, and get answers that match observations. It's good physics. Now apply that model to 3I Atlas. The object is at a distance where solar heating should be modest. The sublimation rate should be low. The resulting tails should be, at most, a few 100,000 kilometers long, probably much shorter. The gas density should be sparse, easily dispersed by solar wind. The mass loss should be negligible compared to the nucleus mass. The whole event should be a gentle, slow process of ice turning to gas. Instead, we see jets millions of kilometers long. We see anti-tails surviving in the solar wind. We see mass loss equivalent to the entire nucleus every month. It's like expecting a garden hose and getting a fire hydrant. No, worse. It's like expecting a garden hose and getting a fire hydrant operating in a hurricane, with the water somehow staying coherent in a tight stream instead of being blown apart. The anti-tail problem is particularly acute. Solar wind at Earth's distance travels at roughly 400 kilometers per second. At 3I Atlas's location, it's somewhat slower, maybe 300 kilometers per second, but still a ferocious wind by any terrestrial standard. For a sunward jet to survive against that wind, the gas density has to be high enough that the outward pressure from the nucleus overcomes the inward push from solar wind. The calculations suggest gas densities around 1 million times higher than typical cometary values. 1 million times. Where is that pressure coming from? Sublimation pressure from water ice is well understood. We know the physics. We know the equations. There's no plausible way to get million-fold increases from sublimation alone, not at these distances, not without the nucleus being absurdly volatile rich and heated far beyond what solar radiation can provide. Let's talk about nucleus size. Based on brightness and reasonable assumptions about surface reflectivity, the nucleus is estimated at 5 to 10 kilometers in diameter. That's actually quite large for an interstellar object. Oumuamua was maybe 400 meters long. Borisov was around half a kilometer. A 5 to 10 kilometer nucleus puts 3I Atlas in the range of major solar system comets. But major solar system comets formed here. They're gravitationally bound to the sun. They've made thousands or millions of orbits. They have stable sources of volatiles deep in their interiors. 3I Atlas came from interstellar space. It's been traveling through the galaxy for millions, possibly billions of years. Cosmic rays should have eroded surface volatiles. Collisions with interstellar dust should have worn it down. The object should be depleted, not hyperactive. And yet, here it is, acting like a comet on steroids. The statistical rarity makes this even more unsettling. Based on surveys of interstellar space, the density of rogue objects, and the size distribution we infer. From other observations, the odds of an object this large passing through the inner solar system are roughly 1 in 100 million per year. 1 in 100 million. That's not rare but expected eventually. We shouldn't be seeing this in human lifetimes. And then there's the orbit. 3I Atlas is on a retrograde trajectory, meaning it's moving opposite to the direction most solar system objects orbit. That's consistent with an interstellar origin. But it's also traveling nearly in the plane of the ecliptic, the flat disk where planets orbit. Most interstellar objects should come in at random angles, isotropically distributed. The fact that it's near the ecliptic plane is another low probability event. Not impossible, but unlikely. Stack up all these improbabilities. Large size, hyperactive outgassing, retrograde orbit, near ecliptic trajectory, arrival during the brief window when humans have telescopes capable of detecting it. Each factor individually is rare. Together, the compound probability drops to absurdly low values. Now, I'm not saying low probability means impossible. Unlikely things happen. That's how probability works. Roll dice enough times, and eventually you'll get 10 sixes in a row. But when you see 10 sixes in a row, it's also reasonable to ask if the dice are loaded. Let's compare with other extreme comets. Comet C/2014, UN 271, Bernardinelli, Bernstein, was one of the largest comets ever discovered, maybe 100 kilometers in diameter. Absolutely gigantic. But at 3I Atlas's distance from the Sun, Bernardinelli Bernstein was barely active. Small coma. No dramatic jets. It behaved predictably. Comet Borisov, the second interstellar visitor, was more active than Bernardinelli Bernstein, but nothing like 3I Atlas. Borisov had a respectable tail, maybe 100,000 kilometers long when it was close to the Sun. It showed outgassing consistent with carbon monoxide and water ice. It was weird in some ways, chemically distinct from solar system comets, but physically it fit within known parameters. 3I Atlas doesn't fit. It's not a matter of degree. It's not 20% more active than expected. It's orders of magnitude beyond any model prediction. And when models fail this badly, Scientists have two options. Option 1. The models are missing something fundamental about cometary physics. Maybe there are processes we don't understand. Maybe interstellar comets can be wildly different from solar system comets in ways we haven't considered. Option 2 is harder to say out loud in professional circles, but let's say it. Maybe it's not a comet. Maybe the entire framework we're applying is wrong, because we're looking at something that wasn't formed by natural processes. Maybe we're looking at technology. Before you roll your eyes, understand that serious scientists are asking this question, not crackpots, not conspiracy theorists. Astronomers with tenure at major universities. Because when every conventional explanation fails, when the math doesn't work, when the probabilities stack up to 1 in 100 million, you have to at least consider alternatives. Extraordinary claims require extraordinary evidence, yes, but extraordinary observations demand extraordinary consideration. So, where does that leave us? Standing at the edge of something genuinely unknown. Staring at data that defies comfortable explanations. Watching an object that shouldn't exist according to our best models. Behaving in ways that challenge fundamental physics. And the question hanging in the air, the one no one wants to ask too loudly yet, is simple. What are we really looking at? When astronomers want to know what something is made of, they don't need to touch it. They don't need to sample it. They just need to look at the light. Every element, every molecule, every chemical compound absorbs and emits light at specific wavelengths. Hydrogen has its signature. Carbon has its signature. Water vapor, carbon monoxide, cyanogen, all distinct. Spectroscopy is the art of splitting light into its component wavelengths and reading the chemical fingerprints embedded in that light. The color shifts we've been seeing in 3I Atlas, red to green to blue, aren't random. They're telling us a story about what's happening on and beneath the surface. Early observations showed red, suggesting carbon-rich dust, organic molecules called tholins, maybe silicate particles reflecting longer wavelengths. This is common in comets that have aged, where solar radiation has cooked surface materials into complex organic tars. Then came the green phase. Green in comets usually means diatomic carbon, C2 molecules, or sometimes cyanogen, CN. These form when ultraviolet light from the sun breaks apart larger molecules like methane or carbon dioxide, and the fragments recombine into short-lived species that glow green. The fact that 3I Atlas went through a green phase suggests intense chemical processing, probably driven by increasing solar heating as it moved inward. Now we're seeing blue. Blue is less common in comets. It often indicates ionized gases, atoms that have lost electrons due to ultraviolet radiation or collisions with solar wind particles. Sodium ions emit blue light. Magnesium ions emit blue-green. Ammonia, if present in large quantities, can also contribute to blue coloration. The blue tint suggests we're now seeing deeper, possibly more volatile-rich layers of the nucleus. Spectroscopic data, the detailed analysis of which wavelengths are present, reveals something unusual. The ratio of carbon dioxide to water is much higher than in typical solar system comets. Solar system comets are usually water-dominated. Water ice is the primary volatile, with carbon dioxide, methane, and ammonia as secondary components. But 3I Atlas seems to have a lot of carbon dioxide relative to water. This could indicate formation in a colder environment than our solar system's comet nurseries, or a different balance of elements in the protoplanetary disk where it formed. There's also unusual metal content. Preliminary spectra show nickel lines that are stronger relative to iron than we typically see. In our solar system, iron is usually more abundant than nickel. They form together in stellar cores and are ejected during supernovae, but iron is more common. A higher nickel to iron ratio might suggest formation near a different type of star, one with a different metallicity or nucleosynthetic history. Think about what this means. 3I Atlas didn't form in our solar system. It formed somewhere else, around a different star, in a different stellar neighborhood, possibly in a different part of the galaxy, possibly billions of years ago. The chemical signatures it carries are fossils of that ancient formation environment. Age estimates are tricky for interstellar objects, but based on dynamical models and the density of rogue objects in the galaxy, 3I Atlas could be 7 billion years old. 7 billion. Our solar system is only 4.6 billion years old. This object predates Earth. It formed when the universe was younger, when galaxies were still settling into their current structures. It's been wandering through interstellar space for eons, a frozen time capsule from a stellar system that might not even exist anymore. Imagine the journey. Ejected from its parent star system, possibly by gravitational interactions with a giant planet, it drifted into the cold darkness between stars. No sunlight, no heat. Temperatures may be 10 degrees above absolute zero. For billions of years, it traveled alone through the void, its volatiles locked in deep freeze, its surface bombarded by cosmic rays and interstellar dust. Then, by pure chance, its trajectory carried it into our solar system. Our sun's gravity bent its path. Solar radiation began heating it. Frozen volatiles started to sublimate. And we, a species of primates who have had telescopes for only a few centuries, happened to be watching when it woke up. Early observations from the James Webb Space Telescope and Hubble are still being analyzed. These instruments can provide much more detailed spectroscopy than ground-based telescopes, penetrating deeper into the infrared, where many molecular signatures are strongest. The data is provisional, still being processed, but early hints suggest complex organic molecules, maybe amino acid precursors, definitely carbon chains. The chemistry is rich and complicated. Thermal history matters. The color progression from red to green to blue likely reflects a sequence of volatile sublimation. First, the surface materials, already processed by cosmic rays and interstellar radiation, come off. Red dust, tholins, carbon residues. Then, as the nucleus heats up, subsurface layers are exposed. Carbon monoxide and carbon dioxide sublimate, creating the green phase. Finally, deeper. Volatiles, ammonia, water ice, more reactive compounds begin to vent, producing the blue coloration and ionized gases. This sequence also tells us the nucleus is compositionally layered. It's not a uniform mixture. There are distinct zones, possibly reflecting different stages of formation or different conditions in the protoplanetary disk where it originated. The outer layers are depleted, processed. The inner layers are pristine, untouched since formation. Isotopic ratios could provide the smoking gun for interstellar origin, but measuring isotopes requires extremely high-resolution spectroscopy, and the object is faint and distant. If we could measure the ratio of deuterium to hydrogen, or carbon-13 to carbon-12, or oxygen-18 to oxygen-16, we could compare those ratios to solar system values. Significant differences would confirm formation in a different stellar environment, possibly around a star with different metallicity or age. But here's the limitation. Current spectroscopy is noisy. Signal-to-noise ratios are low. Atmospheric interference blurs lines. The object is moving, which Doppler shifts the wavelengths. It's rotating, which averages spectral features. And it's far away, which makes it faint. We're extracting hints, clues, suggestions from the data, not definitive answers. Comparing 3I Atlas to Oumuamua and Borisov is instructive. Oumuamua had no detectable coma, no tail, no obvious outgassing when it was discovered. It was classified as an asteroid, not a comet, though later analysis suggested maybe some sublimation was occurring. Borisov was clearly a comet, with a well-developed coma and tail, and its chemistry was distinctly different from solar system comets, confirming interstellar origin. 3I Atlas is more active than Borisov, more chemically complex than Oumuamua, and physically larger than both. Each interstellar visitor teaches us something new about the diversity of objects in the galaxy, and each one is weird in its own way. Oumuamua's strange shape and unexplained acceleration. Borisov's unusual carbon monoxide abundance. 3I Atlas's catastrophic outgassing and million-kilometer jets. None of them behave quite like solar system objects. They're genuinely alien, in the literal sense. They formed elsewhere and carry the chemical and physical signatures of those alien environments. So what does the composition tell us about the natural versus artificial question? Honestly, not much. If 3I Atlas is natural, its chemistry makes sense as an extreme comet from a different stellar system. If it's artificial, we'd still expect it to be made from local materials, whatever elements and compounds were available where it was built. You don't see chemical signatures that scream manufactured. You see volatiles, dust, metals, organics, the same stuff we find everywhere in space. But the jets, the mass loss, the structures, those remain unexplained by chemistry alone. Knowing what something is made of doesn't tell you why it's behaving the way it is. And that's where the real mystery lies. Stand outside on a clear night and look up. If you know where to point your telescope, you might catch a glimpse of 3I Atlas. A faint smudge of light, unremarkable to the untrained eye. But zoom in, increase the exposure time, stack multiple images to pull signal out of noise, and suddenly you're looking at structures that stretch across angular distances equal to the moon's diameter. Structures that translate to millions of kilometers of physical space. The sunward jets are the most perplexing feature. In the standard comet model, tails always point away from the sun. Always. Solar radiation pressure and solar wind are relentless, flowing outward at hundreds of kilometers per second. Any gas or dust ejected from a comet's surface gets immediately swept downstream, away from the sun. It's not negotiable. It's like trying to blow bubbles in a wind tunnel. The bubbles go where the air goes, not where you want them to go. And yet, 3I Atlas has prominent jets extending toward the sun. These aren't small features. They're bright, coherent structures spanning 10 arc-minutes of sky, roughly 350,000 kilometers at the object's distance. The only way this works is if the gas pressure coming out of the nucleus is strong enough to overcome solar wind pressure. That requires extraordinary mass flux, extraordinary velocity, extraordinary energy. Let's talk numbers. Typical cometary outgassing velocities are around half a kilometer per second. That's fast enough to escape the comet's weak gravity and form a coma, but not fast enough to push hard against solar wind. For 3I Atlas to maintain sunward jets, the outgassing velocity probably needs to be several kilometers per second, maybe higher. That's rocket exhaust speeds. That's not gentle sublimation. That's violent explosive decompression. Where does that energy come from? Sublimation of water ice releases energy, but it's a cooling process for the nucleus. The ice absorbs heat to change phase, which cools the surrounding material. Carbon monoxide sublimates at lower temperatures and releases more energy per molecule. But even CO can't explain velocities this high. You need something actively heating the nucleus from within, or some chemical reaction releasing energy, or you need to abandon the natural explanation altogether. Nucleus rotation adds another layer of complexity. If the nucleus is spinning, jets won't point in fixed directions. They'll sweep around like cosmic lighthouse beams. The episodic behavior we see, jets turning on and off, could be rotation bringing active vents in and out of sunlight. But rotation alone doesn't explain the velocities or the mass flux. The episodic nature is real. Some observations show bright, well-defined jets. Others, taken just a day or two later, show the jets significantly dimmed or absent. This suggests the outgassing isn't continuous. It's intermittent, possibly explosive. Pressure builds up beneath the surface, then releases suddenly when a vent opens. The nucleus might be fractured, with fissures that open and close as temperature gradients create stress. The anti-sunward tail, the main structure, is equally strange. It extends 30 arc-minutes, nearly 3 million kilometers. The density isn't uniform. There are bright regions, dark regions, curves, kinks. The tail isn't a smooth gradient. It has texture. This suggests turbulence, variations in outgassing rate, possibly magnetic field interactions with solar wind. Some of the morphology might be due to viewing geometry. If the tail is tilted relative to our line of sight, features that are physically separated might appear overlapping or aligned. As Earth moves in its orbit, our perspective changes, and the tail's appearance changes. What looks like a gap one week might resolve into a bright knot the next. This is why continuous monitoring is essential. Single snapshots can be misleading, but even accounting for geometry, the structures remain anomalous. The tail shows bending, curvature that's sharper than you'd expect from simple ballistic trajectories of ejected particles. Something is shaping the material after it leaves the nucleus. maybe magnetic fields embedded in the solar wind, maybe electrostatic forces between charged dust grains, maybe pressure waves propagating through the gas. Compare this to extreme solar system comets. Comet Hale-Bopp in 1997 had spectacular tails visible to the naked eye. Its dust tail stretched tens of millions of kilometers. But Hale-Bopp was much closer to the Sun, around 0.9 astronomical units at perihelion. It was being roasted by solar radiation, and its tails were proportional to that heating. 3I Atlas is twice as far from the Sun, receiving 1/4 the solar radiation, and yet its structures are comparable or more extreme. Comet Bernardinelli-Bernstein, the largest comet ever discovered, is 100 kilometers across. At similar distances from the Sun as 3I Atlas, it showed minimal activity. A faint coma, maybe 10,000 kilometers across. No dramatic jets. It behaved as expected for a large, cold comet far from the Sun. So size alone doesn't explain 3I Atlas. Big comets can be inactive. Small comets can be hyperactive. But nothing has been both this big and this active at this distance. The physics needs revisions, or we're observing something outside standard physics. Maybe interstellar comets are fundamentally different from solar system comets in ways we haven't anticipated. Maybe they form with different volatile mixtures, different internal structures, different thermal properties. Maybe the billion-year journey through interstellar space alters them in ways that make them unstable when they finally encounter a star again. Or maybe the jets aren't random outgassing at all. Maybe they're directional, controlled, purposeful. The more you look at the images, the more the structures seem deliberate. The sunward jets maintain coherence across hundreds of thousands of kilometers. They don't dissipate. They don't scatter. They push through the solar wind like they're being actively sustained. The anti-sunward tail shows variations in brightness that could correspond to variations in thrust. If you were designing a propulsion system using gas ejection, this is approximately what it would look like. I'm not saying that's what it is. I'm saying the morphology is consistent with that interpretation, and we can't rule it out based on current data. The natural explanation requires physics we don't fully understand. The artificial explanation requires accepting something most scientists find deeply uncomfortable. Neither option is satisfying. The tail grows daily. Observers tracking it report measurable expansion from one night to the next. Material is continuously being added. The structure is dynamic, evolving, alive in a sense. This isn't a static cloud. This is active ejection happening in real time, and we're watching it unfold across millions of kilometers of space. Continued monitoring is critical. Every observation adds data points. Every spectrum reveals chemical clues. Every image captures morphological details. The more we watch, the better we understand the physics, whether natural or otherwise. And the James Webb Space Telescope, with its infrared sensitivity and spectroscopic capabilities, could provide the breakthrough observation that finally explains what we're seeing. But until that happens, we're left with structures that defy simple explanation, jets that shouldn't exist according to conventional physics, and a growing sense that 3I Atlas is showing us something genuinely new. Something that forces us to question assumptions we didn't even know we were making about how objects behave in space. And the question that started as a whisper is getting louder. What if this isn't a comet at all? Let's acknowledge the elephant in the room. The possibility that 3I Atlas might be artificial, not formed by natural processes, not a comet in any conventional sense, but a manufactured object, technology from another civilization, passing through our solar system either by chance or by design. This is the conversation that makes tenure committees nervous. This is the hypothesis that gets you labeled a crackpot, at least until enough data accumulates that ignoring it becomes more uncomfortable than considering it. But here's the thing. When every natural explanation requires unprecedented physics, when the statistical odds drop to 1 in 100 million, when respected scientists start quietly asking, what if, then the conversation deserves to happen. The natural hypothesis is straightforward. 3I Atlas is an extreme interstellar comet, larger and more volatile-rich than any comet we've previously observed. It formed in conditions very different from our solar system, possibly around a star with different metallicity, or in a protoplanetary disk with unusual chemical composition. Its hyperactivity is real, but explicable through some combination of high volatile content, internal heat sources we don't fully understand, and structural properties that make it unstable when heated. This explanation requires us to expand our understanding of cometary physics, but it doesn't require us to abandon fundamental assumptions about how nature works. Comets can be weird. The universe is vast. We've only observed a tiny sample of possible cometary types. Maybe 3I Atlas represents the tail of a distribution, a rare but natural extreme. The technological hypothesis is more provocative. Avi Loeb, the Harvard astrophysicist who previously suggested Oumuamua might be artificial, has calculated that the mass loss rate of 3I Atlas, around 50 billion tons per month, represents less than 1% of the object's total estimated mass if you assume it's actually much larger than the visible nucleus. For an engineered propulsion system using gas ejection, losing 1% of your mass to achieve acceleration is perfectly reasonable. Rocket engines do this. Ion drives do this. Any reaction drive trades mass for momentum. The jets could be thrusters. The anti-sunward tail could be a main propulsion exhaust. The sunward jets could be attitude control, steering, course corrections. The non-gravitational acceleration, the deviations from a pure gravitational trajectory, could be evidence of active propulsion rather than random outgassing. The episodic behavior could be burns, periods of active thrust followed by coasting. The statistical improbability argument cuts both ways. Yes, 1 in 100 million odds are tiny, but they're not zero. Somewhere in the galaxy, at any given moment, there are probably thousands of interstellar objects passing through stellar systems. We only notice the ones that pass through ours. Selection bias makes rare events seem rarer than they are. But if you flip the argument, if you assume technological objects are out there, wandering the galaxy, then the odds of encountering one aren't necessarily that much lower than encountering a natural extreme. If a civilization builds self-replicating probes and sends them out to explore, and if those probes have been multiplying and spreading for millions or billions of years, then the density of artificial objects in interstellar space could be non-negligible. Not common, but not absurdly rare either. Mainstream experts urge caution. Brian Cox, the physicist and science communicator, has emphasized that extraordinary claims require extraordinary evidence, and we don't have that evidence yet. The observations are consistent with a natural object, even if they're at the extreme edge of what we'd expect. We shouldn't jump to conclusions based on incomplete data and statistical arguments. And that's fair. That's good science. You don't claim discovery of alien technology based on anomalous brightness curves and unexplained jets. You exhaust all natural explanations first. You gather more data. You build better models. You remain skeptical. But skepticism cuts both ways. You also can't dismiss a hypothesis just because it makes you uncomfortable. If the data genuinely can't be explained by natural processes, if every model fails, if the physics simply doesn't work, then at some point you have to consider alternatives. Not accept them uncritically, but consider them seriously. Social media has amplified the speculation. The moment the November 9th images went public, Twitter and Reddit exploded with theories. Some reasonable, some absurd. Claims that 3I Atlas is a generation ship, that it's a von Neumann probe, that it's a derelict vessel, damaged, leaking atmosphere. The signal-to-noise ratio in public discourse is terrible, and it poisons the well for legitimate scientific discussion. This is what happened with Oumuamua. The initial observations were genuinely strange. The cigar shape, the tumbling rotation, the unexplained acceleration. These were real anomalies. But the speculation got out of hand. Popular media ran headlines about alien spacecraft. Scientists who suggested natural explanations were accused of close-mindedness. Scientists who suggested artificial explanations were accused of attention-seeking. The whole discourse became polarized and toxic. We need to learn from that. We need to hold space for genuine uncertainty without tipping into unfounded speculation. 3I Atlas is strange. The data is weird. We don't have a complete explanation. Those are facts. Whether the eventual explanation is natural or artificial is an open question, and we should be comfortable saying we don't know yet, without feeling pressure to choose sides prematurely. Historical context matters. There's a long history of astronomical discoveries that seemed inexplicable at first, but turned out to have natural explanations. Pulsars were thought to be alien beacons when first discovered. They're actually rotating neutron stars. Fast radio bursts were mysterious transients. They're now understood as natural astrophysical phenomena, though the exact mechanisms are still being worked out. Nature is creative. Nature produces phenomena that seem designed but aren't. Probabilistic reasoning is tricky. 1 in 100 million odds sound impossible until you remember that there are hundreds of billions of stars in the galaxy and trillions of objects orbiting those stars and drifting between them. Multiply 1 in 100 million by a trillion, and suddenly unlikely events become near certainties somewhere, sometime. The question isn't whether rare events happen. The question is what we infer when we happen to observe one. Extraordinary claims do require extraordinary evidence, but extraordinary observations demand extraordinary attention. 3I Atlas is extraordinary by any metric. Largest interstellar object observed, most active, most structurally complex. Whether that extraordinariness implies natural rarity or artificial origin is the question we're trying to answer. And here's the uncomfortable truth. We might not get a definitive answer. The object will continue its trajectory through the solar system, eventually fading from view as it recedes into interstellar space. We'll have a few months, maybe a year, of good observing conditions. Then it's gone. If we don't gather decisive data during that window, we're left with ambiguity. Suggestive but inconclusive observations. Anomalies that hint at something profound, but don't prove anything. So what should we think? I'd argue we should think critically and hold multiple hypotheses simultaneously. Natural extreme comet remains the most parsimonious explanation, the one that requires the fewest new assumptions. But artificial origin remains a logical possibility that can't be dismissed without evidence. The responsible position is epistemic humility. We don't know. We're trying to figure it out. And we should follow the data wherever it leads, without preconceptions about what the answer has to be. Because ultimately, whether 3I Atlas is natural or artificial, it's teaching us something profound about the universe. If it's natural, we're learning that comets can be far stranger than we imagined, that interstellar space harbors objects with properties outside our current models. If it's artificial, we're learning we're not alone, that intelligence exists elsewhere, that technology can cross the gulfs between stars. Either answer reshapes our understanding of reality, and both answers are extraordinary. The discovery of 3I Atlas wasn't an accident. It was the result of systematic sky surveys designed to catch transient events, moving objects, anything that changes from one night to the next. The Atlas survey, Asteroid Terrestrial Impact Last Alert System, uses robotic telescopes to scan the entire visible sky every few nights, looking for asteroids that might threaten Earth, supernovae exploding in distant galaxies, and yes, interstellar visitors passing through our cosmic neighborhood. But here's the scale problem. Every night, Atlas generates terabytes of image data. Millions of stars, galaxies, asteroids, something like 10,000 moving objects detected per night. A human astronomer can't possibly review all of that. You'd need thousands of people working around the clock, and even then, you'd miss things. This is where artificial intelligence enters the story. In 2025, machine learning models are integrated directly into survey pipelines. Neural networks trained on millions of astronomical images can identify anomalies in milliseconds. They flag objects that move in unusual ways, that brighten unexpectedly, that have spectral properties outside normal distributions. The AI doesn't replace human astronomers. It acts as a filter, a first pass that identifies candidates worthy of human attention. 3I Atlas was flagged by one of these systems. The algorithm noticed an object moving on a hyperbolic trajectory, entering the solar system from interstellar space, with brightness variations that didn't match typical asteroid or comet profiles. It sent an alert. human astronomers followed up, and the rest is unfolding history. This is the future of astronomy. Not replacing humans with machines, but augmenting human capability with computational tools that can process data at inhuman speeds. The AI doesn't understand what it's looking at, not really. It's pattern matching, statistical analysis, trained on labeled examples to recognize outliers, but it's fantastically good at finding needles in haystacks. Detection speed matters. The sooner you identify an unusual object, the more time you have to study it. With 3i Atlas, we had months of advance warning before it became dramatically active. That allowed observatories to schedule time, plan observations, coordinate spectroscopy. If it had been discovered only after the November 9th expansion, we would have missed critical baseline data. AI is also improving real-time trajectory analysis. Once an object is detected, machine learning models can predict its future path, calculate optimal observation windows, even suggest what kind of measurements would be most informative. This closes the loop between detection and scientific follow-up, making the entire process faster and more efficient. Pattern recognition is another frontier. When you have decades of sky survey data, you can train networks to identify trends that humans would never notice. Subtle correlations between orbital parameters and physical properties. Statistical regularities in how objects evolve over time. The AI can discover relationships in the data that lead humans to ask better questions and develop better theories. In 2025, there are examples beyond 3i Atlas. AI systems have flagged unusual stellar flares, transient events that might be tidal disruption events, where stars are torn apart by black holes, gravitational microlensing events that reveal rogue planets drifting through the galaxy. Each discovery is a data point, a piece of the cosmic puzzle that we're assembling with increasing speed. The rate of interstellar object discovery is likely to increase. Before Oumuamua in 2017, we had never detected an interstellar visitor. Then Borisov in 2019. Now 3i Atlas in 2025. The intervals are shrinking. Surveys are getting better. Algorithms are getting smarter. We might be entering an era where discovering interstellar objects becomes routine, where we catalog dozens or hundreds over the next decade. And that's where things get interesting. If interstellar objects are common, if we start building a statistical sample, we can answer questions that are currently just speculation. What's the size distribution? What fractions show cometary activity? Are there distinct populations, rocky versus icy, active versus inactive? And crucially, do any of them show signatures that can't be explained by natural processes? AI could potentially identify engineered objects before humans recognize the signatures. If there are subtle patterns in how artificial objects move, accelerate, or emit radiation, patterns that are statistically distinguishable from natural objects, machine learning could detect them. The algorithm wouldn't know it's looking at alien technology. It would just flag the object as anomalous. But that flag could be the first hint that something profound is in the data. Spectroscopy is being enhanced by AI as well. Analyzing spectra is traditionally a labor-intensive process. You identify absorption and emission lines, match them to known elements and molecules, model the physical conditions that produce those lines. Machine learning can automate much of this, processing spectra in seconds that would take humans hours. This allows rapid chemical characterization of newly discovered objects, which is essential when observing windows are limited. Citizen science plays a role too. Projects like Galaxy Zoo have shown that distributed human effort can accomplish scientific tasks at scale. For 3i Atlas, amateur astronomers around the world are contributing observations. They're imaging the object, measuring its brightness, tracking its position. This data supplements professional observations and provides continuous monitoring that no single observatory could achieve alone. AI helps coordinate citizen science efforts. Platforms can automatically aggregate amateur observations, cross-check for quality, combine data from multiple sources to improve signal-to-noise ratios. The result is a global, distributed telescope network operating in real time, with AI as the central nervous system integrating inputs from hundreds of observers. Social impact matters. The more people participate in astronomy, the more the public understands and values space science. When amateur astronomers contribute to the discovery and monitoring of interstellar objects, they become stakeholders in the research. They're not passive consumers of science news. They're active participants in the process of discovery. The speculative outlook is tantalizing. As AI becomes more sophisticated, as training datasets grow, as models become better at distinguishing subtle patterns, we might reach a point where algorithms can predict which objects are worth studying based on minimal initial data. See an object for one night, feed its characteristics into a model, and get a probability estimate for how scientifically interesting it will turn out to be. This could revolutionize how we allocate telescope time and prioritize targets. There's also the possibility, uncomfortable for some but worth considering, that AI might identify potential technosignatures before humans do. If an object moves in a way that's statistically consistent with propulsion, if its spectrum shows emission lines that suggest industrial processes, if its trajectory includes course corrections, an algorithm trained on vast datasets might flag these patterns. The interpretation would still require human judgment, but the initial detection could be automated. This is one of the reasons 3i Atlas is so important. It's a test case. It's pushing the boundaries of what we think is possible for natural objects. It's generating massive amounts of data that will train the next generation of detection algorithms. Whether it turns out to be an extreme comet or something else, it's teaching us how to recognize and characterize rare, anomalous objects in space. And the next interstellar visitor might arrive while we're still trying to understand this one. With improved detection systems, we could have multiple interstellar objects under observation simultaneously. That would allow comparative studies, looking for commonalities and differences, building a taxonomy of interstellar visitors. Are they all weird in the same ways, or does each one present unique anomalies? The tools are changing. The game is changing. We're entering an era of big data astronomy where discovery is limited not by our ability to collect data, but by our ability to process and interpret it. AI is the key that unlocks this new paradigm. And 3i Atlas, discovered by an automated survey, flagged by algorithms, studied by a combination of professional and amateur astronomers using AI-enhanced tools, is the prototype for how astronomy will function in the 21st century. We're not just watching the sky anymore. We're drinking from a fire hose of cosmic information, and AI is the tool that helps us find the drops that matter.